Started. Okay. Good afternoon, everyone. So we'll continue with our strain chapter. So yesterday we had discussed quite a few things as part of the preamble towards the discussion of strain, and today we'll continue with strain. Uh, just a small note that at the very end of yesterday's class, when I was talking about the magnitude of a vector, I had written the vector and then I had written equal to the magnitude. So please make that correction. So I had written something like a vector is equal to ax I hat plus ay j hat plus az k hat. When I was reviewing the video yesterday, I saw that after that I wrote equal to a dot a. That doesn't make any sense. Okay, so please make that correction. So so for strain, we said that E is equal to d small x vector magnitude minus d capital X vector magnitude divided by d capital X vector magnitude. So this definition is motivated but by what we had studied already in our +2. Prior to this, we had also obtained this expression. So please check if this is correct. Okay. Now, what we are going to do is to find out the magnitude of this d small x vector. And the way that we are going to do it is because, as we said yesterday, that square root was a problem, and we would remove that problem by squaring it. Okay. So what we are going to do today is to start with this dx d small x vector magnitude square of that, and immediately we recognize that this is nothing but dx vector dotted with itself. All right. If this is all right, then we can. Do you want to ask something? So if this is all right, then after this we can pick up our speed a little bit, because after this is complete algebra. Okay. So this, I hope this is all right. Okay. Now you see, what we are going to do is to substitute this expression over here. Okay. So this is what? D capital X vector plus transpose of this whole thing multiplied with the same thing. So we have to do this multiplication. Now, before we do the multiplication, what we'll do is we'll take this transpose inside the bracket. So just one step before that. So note what I have done here is I have taken the transpose inside, and this is like A matrix times B matrix, and the whole transpose of that will be B transpose into A transpose. That's what I have written here. So AB whole transpose is B transpose A transpose. Okay. Now what we are going to do is do the multiplication. So let me move over to this side. So this is the entire multiplication. Now, before we proceed any further, uh, we will take a proper look at this last term. So please note that if you expand all of these things, like we had done the entire matrix, the explicit matrix representation, then you will see that it will contain terms. This one will contain terms like del u del x, del u del y, del v del x, del v del y, all these things. This also will contain terms like that, del u del x, del v del y, all these things. So when you actually multiply them out, what will happen is that it will contain, so this term, what is so special about this thing? This is quadratic in the partial derivatives. Okay, this is multiplied with this. Similarly, if you have del u del x multiplied with del v del y, these are quadratic terms. But in all the other terms, you note that they may be multiplied with this dx thing, but as far as the partial derivatives of the displacements are concerned, they are sitting alone. They are not multiplied, okay? So there is no repetition or multiplication of the partial derivative terms over here. There is no multiplication of the partial derivative terms over here, okay? So what we'll say is that we are going to consider these as the higher order terms. Okay, earlier we had already ignored the higher order terms in the Taylor series expansion. So it is at the same level of abstraction. Okay, so everywhere that we get quadratic terms and higher, we are going to drop those terms. So I am now writing equal to, but this is a qualified equal to, in the sense that this is actually an approximation where the higher order terms are being dropped. So what we'll have now, please check if this is correct, neglecting the higher order terms, of course. Okay. Now what we are going to do is, we are going to introduce a half for apparently no rhyme or reason. Okay. So yesterday, Akshat had mentioned this when we were first starting to discuss the gradient of u term. The gradient of u, okay, this you had encountered something similar to this in fluid mechanics also, where you had the gradient of the velocity vector. Here it is the gradient of the displacement vector. Now, whatever it may be, it is a matrix. As we have written here, it is a matrix. And any matrix can be decomposed into its symmetric part and its antisymmetric part. This you know. Okay. So, if I put a half in front of this, does it not become, this particular combination, does it not become the symmetric part of the gradient of U matrix? Okay, so what I'm saying, in case you have forgotten, is that suppose you have any matrix A. So this can be written as half of A plus A transpose plus half of A minus A transpose. This is an identity. The first part is what is referred to as the symmetric part. Okay, you don't have to take my word for it. You take the transpose of this entire thing, you will get this back itself. And this is referred to as the antisymmetric part. because if you take the transpose of it, you'll get the minus of this thing. Okay, so this is the antisymmetric part. So recognize that if you consider this as the matrix, then this term, this entire combination is the symmetric part, provided you have a half in front of it. Okay, so we will artificially introduce the half and of course adjust it by multiplying a 2. Absolutely okay. Now, this particular combination, this symmetric part of the gradient of the displacement vector, we will call this by a special name. Okay. Does anyone recognize what this is? This half of the gradient of u plus gradient of u transpose, we'll call this by a special name. No? No problem. So we'll call that as the strain matrix. Okay, that itself is the strain matrix. So what we'll say is, define. What is this colon saying before the equal to? So this is not an equation. Okay, whatever I am going to write, this epsilon is equal to this is not an equation. Okay, this is a definition. I am choosing to define it this way. Okay, so please note that I have again put 2 tildes beneath it. Okay, so this represents that this is going to be a tensor. Without going into any details of it, I'm just putting it, leaving it here. Okay, so in the same way that the stress was a second order tensor, this also is a second order tensor. But again, we are not going into the details of it. If some of you are interested in knowing why it is a tensor and what is the meaning of that, you please reach out to me. I will give you some very easy notes, not like PhD level notes, like second year, third year type notes. So earlier when we used to teach mechanics of solids to the third year guys, not the previous curriculum, the previous to previous curriculum, it used to be in the third year. So there we had some mathematical preliminaries, so I'll share those notes with you. Okay, let us not go into those details now. So the matrix representation of it okay, just the same thing. Okay, so that is this. So we'll write it properly now. So remember what was this thing that we were doing? This is the d small x vector magnitude square. This thing came out as, do you recognize what this is? This is d capital X vector magnitude square. Plus, what I have now is this d capital X vector matrix transpose epsilon matrix.
The second one you have written that. The first one.
Sorry?
First equation.
This one? This is a definition.
What is the meaning of that?
This transpose.
No, but that is not a matrix.
This is not a matrix. So you can have a transpose of a tensor also. Okay? So this has its origin somewhere, right? So that is the origin. You can have a transpose of a, so we don't understand it in terms of this, but when writing and when doing the actual programming, so many of these things have to be actually coded up. okay, for example, as part of a finite element methods framework, so then most of these things are not most of the things, everything is done in terms of matrix only. Okay. Okay. So we have these things. Now, I just want to point out something very, very important. You please note that here we had started out with this epsilon. This epsilon and that epsilon are not the same thing. Okay, why not? First of all, you note that what is this? This is a scalar. Okay, this is a scalar entity. That is a tensorial entity. Okay, that epsilon with two tildes beneath it. Okay, and if you write out the matrix representation of it, it will have 9 elements. Okay, so we'll see that. Now, what we want to do right now, yes, let's take a look at those things. So this epsilon, I will not do the line by line detail of it. I will write down the answers. You go to your room and you verify whether what I'm writing makes sense or not. So till now, we have taken a path which is completely divergent from Beer and Johnson. But now we are going to converge. Okay. This is the expression. Now, yesterday I had already written the entire expansion of this gradient of U vector matrix. Okay, the 3 rows and the 3 columns I had written. You take those things, you take the transpose of it, and you write down the entire thing with laborious detail. Once you do that, what you are going to get for each of the elements over here are as follows. Okay. There is no rocket science here. Okay. If you just expand it, you will get it. Okay. So please verify all of these things. Now please note that this expression of epsilon xy that you have, if you consider the epsilon yx, it is just going to be del v del x plus del u del y with a half in front. Similarly, the epsilon zy will be del w del y plus del v del z with a half in front, and epsilon zx will be del u del z plus del w del x with a half in front. So, you see, by the very definition, by the way that we have chosen to define our strain matrix, it turns out to be a symmetric matrix. Okay, because epsilon xy is equal to epsilon yx. Epsilon yz is equal to epsilon zy, and epsilon zx is equal to epsilon xz. Okay, so by definition, the strain matrix is symmetric. Unlike the stress matrix. The stress matrix by definition is not symmetric. Only when you invoke the condition that you have moment equilibrium and then you do a little bit of exercise, that you manage to obtain that tau xy is equal to tau yx, tau yz equal to tau zy, and tau zx equal to tau xz. And that too, I have told you that for certain materials, it doesn't hold true. For example, when you have something called body couples, those are absolutely outside the scope of your syllabus, but it is important to recognize that you do have conditions where the stress matrix may not be symmetric. But the way that we have defined the strain matrix, it is always symmetric. Now, please note my words. Okay, I'm not just saying things just like that. Every time I'm saying that we have chosen to define our strain matrix in this particular fashion. Now, if we have chosen to define our strain matrix in this fashion, it means that we could have as well chosen to define in some other fashion, and that is actually true. Okay, so if you open the Wikipedia page on strain, you will see that there are varying kinds of definitions of strain. None of those are part of our syllabus, and you do not have to know them officially also, unofficially also, but I'm just telling you for your general edification. There is another very sentimental reason for us to know about it. There used to be a very famous professor, not in the mechanical engineering department of IIT Kharagpur, but in the maths department. So his name was Professor B.R. Seth. Okay, B.R. Seth, Bhoj Raj Seth. Back in the day, okay, 50s, 60s. I mean, he passed away a long time ago. So he actually came out with a very useful measure of strain. He generalized a lot of things. So his name is immortalized in these definitions of strain. Okay, so there is something called a Seth measure of strain. So if you just Google it, you will find it. Okay, so that is something we as KGPN should be proud of. Okay. Okay, so we have all of these things. Now, when you are doing problems, when you are actually doing problems, it is these things which are going to be operationally useful. Okay, those things are important for your conceptual understanding. All of these things which I have presented to you, those are important for your conceptual understanding. But for your operational problem solving purposes, it is these things which are going to be again and again necessary. Okay, so this is not by the way. Okay, this is going to be absolutely important. Now let us come back to this thing. So what we'll do now is we'll try to, please note that my original idea was that I will try to obtain that scalar epsilon. That promise has not yet been fulfilled. Okay, so we have to get back on my way to fulfilling that promise. So what I will do here, you see something is taking shape here. Okay, so when we are doing these derivations, don't just take them at face value. At every step, before looking at the next step, try to think that the persons who first did these things, what kind of motivation they might have had in proceeding. Okay, to recognize that this particular combination is the dot product, it is okay. A dot product is a magnitude square, that also is okay. But see, something very nice we can find out from here, that ultimately in order to arrive at that epsilon thing, we want the combinations d small x vector magnitude and d capital X vector magnitude. How can we extract the d capital X vector magnitude from these things? You know the answer actually. So see, if you have any vector, okay, if you have any vector, how do you extract the magnitude out of it? Yes, you take right, but this is mathematically incorrect, what you have done. So what is missing? Right, direction. So what do I have to put here? I have to put the unit vector which is oriented along this A vector. Okay. Okay, so that is the very simple concept which you know from your class 11 and 12, which we are going to utilize here. So it is as follows. From this, I will take out one dx vector magnitude. I will get this. From here, what will I get? I will get this capital N vector transpose. What is this capital N vector? This is the unit vector oriented along the d capital X vector, meaning that this n hat is what? Is the unit vector between the points P and Q. Remember the three-dimensional potato we drew yesterday? If you don't remember, look back at your notes. Okay, so in the initial configuration of the three-dimensional potato, we had the 2 points P and Q. Okay, so this n hat is the unit vector oriented from P to Q. Then we have this epsilon that remains unchanged. Now from this dx vector, I will take out another magnitude. If I take out another magnitude, it gets multiplied here, so this becomes a square. And then we have this thing. Yes, very good. Whoever said common, we are going to take a common. So here you see this d, sorry, printing mistake. Okay, so we'll take the d capital X vector magnitude square common. Now you see it has started to shape up beautifully, especially if you remember some things from the stress chapter. Some of you may be already recognizing where this is going. So what we'll do is, we will take this thing downstairs on the left. Okay. Let me erase all of this. Right? Okay. Now see, this is what? So remember, our epsilon we had chosen this definition. Okay, which means that okay, all right, which means this thing square means that is 1 plus epsilon whole square. Okay, right? Now what we are going to do is we are going to expand the left hand side. Okay. Now who can tell me what I'm going to do next? Epsilon square I'm going to drop. So everywhere that I get a quadratic, I'm going to drop it. Okay. So this you drop. So 1 and 1 cancel. So ultimately what you are going to get is this thing. Do you recognize what this is? By analogy with what happened in what we had managed to find in the stress chapter. If you look back at the stress chapter, this was what? Is an expression similar to this. Okay, this quadratic form, you had the stress matrix here. And what was the expression for that? So that was the normal component of the stress. Okay, the Tn, very good. Okay, so correspondingly, so just like in the stress chapter, when instead of the strain matrix here, you had the stress matrix, we called this particular combination, this quadratic form, as the normal component of the traction vector. In a similar fashion, this is the normal, or the normal, I shouldn't say component, but this is the uh, normal engineering strain. Okay, let's call this the normal engineering strain. Okay. If this is the normal engineering strain, then surely there must be a shear engineering strain. Okay, there is. Okay, there absolutely is. Now, what we are going to do, so again, see, the end result is the same as in the stress chapter, but the route that we had taken to arrive at it is completely different. It's a completely different story compared to the stress chapter. So in a similar fashion, for the shear strain also, the story is going to be different. Okay, all this while we had been talking about the geometry, we have to continue to talk about the geometry. So what we'll do is, we'll take two little proofs, okay, two very short proofs, and ultimately we'll see suddenly the shear strain has come. Okay, so have a little faith. So the first thing that we are going to discuss is this little topic called you have to be a little bit patient, okay? Within 15-20 minutes, you will see something nice will happen. So change in the direction of an elemental line segment. So till now, we have considered two line segments. One of them was PQ, the other was P dash Q dash. Okay, so we had this PQ. And in the deformed configuration, this turned out to be P dash Q dash. Okay, so comparing these two things, we managed to find out the engineering strain. So again, we are just keeping that, all that discussion from prior in one side of our brain, and we are going to investigate this. So the question is like this, that given n hat, what is n hat? N hat is the unit vector along the PQ. To find small n hat. What is the small n hat? It is the unit vector along the P dash Q dash. Okay, so that is why the name of this topic is change in the direction of an elemental line segment. Okay, all right. So how do we go about doing this? Yes, we have all the equipment in our hand. Okay, so this was our equation that we had found out earlier. Okay, so from all those things which we had kept at one side of our brain, we are extracting this. Okay. Now, just like before, we are going to extract the magnitude and the unit vector out of it. Okay. So, what is the magnitude? This is this. This small n hat is the answer that we are seeking. Similarly, over here, this is the magnitude, this is the n hat. You have to write the matrix. And here, of course, okay, ठीक है? We want to find out this n hat, right? Let us find out this n hat. Sorry? Oh, sorry. Yeah. So I have made a mistake in the sense that I have picked half of something from and half of something other. So this actually, so please make this correction. This part we had obtained from the square of it, right? So please tell me in terms of the gradient of u, d capital X. Okay. Sorry. Okay. So again, we can extract the magnitude out of it, and then we have okay. So we can now find out this n hat matrix. So here what I will do is I will take this n hat matrix common. Do you recognize what this is? Identity matrix. Okay, because I have taken it common, something has to stand here, right? I cannot write 1. Okay, because everything is in terms of the matrix. So this is the identity matrix. Okay, and can you tell me what this thing is? This is the engineering normal strain with a +1. Okay, so this is nothing but all right. So this is the first little discussion that we wanted to have. Next, what we are going to do is we are going to consider the change. Acha, you right. I'll discuss after that. This is the next topic. Change in the angle between two elemental line segments. The first was the change in the direction of one line segment. Now we are going to consider two line segments. There will be a certain angle between them. We are going to consider that under some deformation, how those two line segments, I mean the angle between them changes. Okay. So this is PQ, and then we'll have another thing which is this PR. Okay. The angle between them in the initial undeformed configuration of the body. Okay, in the initial undeformed configuration of the body, this is theta, and after the deformation has taken place, we'll say that it is going to be something like this. This angle is going to be theta dash. Okay, so what is given to us is theta, and what we have to find is the theta dash. Okay, now these two topics are not disparate. Whatever we have obtained as the result of the first topic, we are going to utilize that result over here. So you see, we have the direction change, the direction change for one line segment. Now, if you have the unit vector, now utilizing the unit vector, can you not find out the angle? So this is capital N hat 1 and this is capital N hat 2. Okay, so I will write that. I'm writing with a superscript but with a bracket so that you do not mistake it as a power. Okay, so this is not n hat to the power 1. This is the superscript 1 just to identify that it corresponds to the elemental line segment PQ, and this is 2, so it is not a square. This is just to identify that it is the second line segment. Okay, similarly over here I will have the n hat superscript 1 and the n hat superscript 2. So if I want to find out something about the theta dash, what should I do? I'll take the dot product. Okay, this is just like class 11. So cos theta dash, because I want to find out theta dash, directly I cannot find out, so I'll find out through the root of cos theta dash. So cos theta dash will be equal to n1 hat dotted with n2 hat. Okay, and in terms of the matrix representation, this is going to be this. So A dot B is A transpose B. Fine. The moment we have this in terms of the matrix representation, we can look at this expression. In the previous topic, we had obtained already the unit vector small n hat in terms of the capital N hat. Okay. Now, before I write anything, all of you just put down your pen for 10 seconds and listen to me very carefully. When I am talking about the small n hat or the capital N hat, I am actually referring to the line segment with which I am concerned with. If I am talking about the PQ, it is with the superscript 1. If I am talking about the PR, it is with the superscript 2. But when I am talking about the gradient of U, what is it about? Is it about any line segment? No, it is not. Because you note that when we write anything like a del U del X, a del V del Y, all these things, these pertain to a single point. Okay, these pertain to a single point. All the derivatives, so going back to your fundamental concepts from class 11, all the derivatives and everything, those pertain to a single point. Okay, so all these things which are contained, all the partial derivatives which are contained within this matrix, they refer to a single point. Which point is that? This is the point P. Okay. It is by using this unit vector that we are identifying along which direction we are concerned with. But the gradient of u is pertaining to the point P. Remember this. Okay. What about this epsilon? Does it refer to the point P, or does it refer to any one particular direction? Definitely one direction. Engineering normal strain, right? It is found out using information which is available at the point, but you can only find out its value corresponding to a certain direction. Okay. So please check if this seems all right. What I have done here is that I have utilized this formula. But when utilizing this formula, I have taken care to put the correct subscripts at the appropriate places. Here, I need the superscript. I need the proper superscript. Here also, I need the proper superscript. But here, I don't need the superscript because it pertains to the point P. Doesn't matter whether it is the PQ or the PR. Okay. Similarly, here I need the superscript 2 because it corresponds to this n hat 2, small n hat 2. In the denominator also, this epsilon is there, this engineering normal strain is there. This must contain the superscript 2. Okay. But this one doesn't require. Okay. This is pertaining to the point P. So if we have understood this thing, then very quickly we can, so the hard part is over actually. So what we'll do is, those 1 plus epsilon 1 and 1 plus epsilon 2 which are present in the denominator, I will take them to the left hand side. Okay, so I'll multiply them with the cos theta dash. Lots of approximations and droppings are going to come. So just brace yourself. Now, we have this thing, right? This entire thing. I'm going to multiply that. Okay. So I may skip 1 or 2 lines in between, so please don't mind. Actually, let's keep this like this. There, can you see that I have made a mistake here? No? Is the placement of this n hat correct? Yes. It should be post multiplied. Okay, it should be post multiplied. So, because you see this is gradient of u matrix times the n hat. So it should be like this. I'll correct it. Not a big deal, but I'll correct it. Okay, so here also I'll make the correction. So I'm multiplying it again. So the reason is this is the form that I wanted for this particular expression. I wanted it cleanly in terms of the n hat. But for doing all those internal manipulations, it is better that I stick to this explicit form. So this is with the transpose. And then for the other term, I have n hat 2 plus gradient of u vector Okay, now I'm ready to do the manipulations. So this is just n1 hat transpose plus n1 hat 1 transpose gradient of u transpose multiplied with whatever was there in the previous line. Now I'm going to do the multiplication n1 with this n2 but with the transpose. Next n1 transpose gradient of u n2 plus these things. Plus, what do you think is going to happen for the multiplication of this with this? Higher order terms. Why? Because you have the gradient of u here, you have the gradient of u here. When we multiply them, again you are going to end up with quadratic terms involving the displacements. So plus higher order terms. What is this? Do you recognize? This is the dot product between the n1 and the n2. I'll make it larger because I've noticed that in the video, these dots are not coming out clearly. Plus, you see what is happening over here. Maybe I have, there is a transpose missing somewhere, right? Where this here. Okay. So do you recognize what is happening here? So again, I have this combination gradient of u plus gradient of u transpose. Okay. So I'm taking it common and then I'm replacing it by twice epsilon. Okay. Now, who can tell me from this, how does the shear strain come? Okay, you take a 5-minute break and think about it. Stop the